Uh, okay. Local Hamiltonian. So local Hamiltonian just means it's sort of like you have like a magnetic field that's slightly rotating things when you're sitting around, but it's not supposed to be there. Ideally, a local stochastic noise. So local stochastic noise means that on any given time period, every qubit has some fixed probability here. I'm saying epsilon of some error being introduced. And the interesting property here is that if you take 2 qubits, the probability of both of them being messed up is epsilon squared. If you have 3 qubits, the probability of all 3 of them being messed up is epsilon cubed. This is important because if you had probably epsilon squared of 10 qubits being messed up, like that's not small enough. You really want it to decay. It doesn't have to be this exponential. There's theorems that give you some tail. But ideally, you'd have really independent noise and independent qubits. All right, so what do we actually, in practice, I mean, there's interesting noise models. So what do I have here? Right, so I think in practice, we don't actually understand the noise very well in these systems, as far as I can tell. I mean, if you try to talk to them, you never get straight answers, which I assume means they don't understand it that well. If they understood, they'd fix it. And also, even if we did understand the noise very well, it wouldn't necessarily be that helpful for a theorist, because you can't simulate a quantum system efficiently. Yeah. So if somebody told you this is my noise channel, and they say, okay, let me run this like on the Google machine, 50 odd qubits, 54 qubits, whatever. You can't simulate that on your classical computer. That was actually the point of their Nature paper. So it wouldn't, I don't know, it's not clear how helpful that would be. But these stochastic error models are actually quite easy to simulate, because in the stochastic error models that we talk about, we say with probability p, you have some Pauli operator is applied. So like with probability p, and a z error is applied, with probability 1 minus p, the identity is applied. So that's called a stochastic Pauli channel. And this is what we usually use in our simulations and stuff. And the reason is because it's relatively easy to simulate. You just run it on your supercomputer or on your laptop, whatever. And you introduce errors at randomly according to this model. And why does that work? Well, it only works if you're only doing stabilizer operations. So if you're only doing stabilizer operations, then you can use Gauss-Knill stabilizer algebra to simulate the system with Pauli errors instead of actually having to keep track of a 2 to the 54 dimensional system. Okay. Is that part of your question? No? Yeah?
So actually, it's instead of the depolarizing noise, so which kind of other noise can be simulated on classical computer efficiently?
Okay. Yeah. So, I mean, basically, the only kinds of noise that can be simulated efficiently are stochastic Pauli channels, basically. And so these all have a similar form. So this is the depolarizing noise channel. It looks like this. Depolarizing noise on a 1 qubit density matrix with probability p. It says with probability 1 minus p, nothing happens. And these are the Pauli operators are the cross operators. So with probability p over 3, an x error occurs. With probability p over 3, a y error occurs. And with probability p over 3, a z error occurs. And a different way of saying this, these are equal to each other. A different way of saying it is with probability 4/3 p, 1 minus 4/3 p, nothing happens. With probably 4/3 p, so these 3 plus 1 more, the state is completely mixed. So this is not rho anymore, it's just the identity matrix. So the qubit's completely lost. And you just have to be a little bit careful. I think most papers use this parameterization, so this is what they call p. But some papers will call this parameter p, and so you're off by a factor of 3/4 or 4/3 or whatever. Right, okay. So what this does in the Bloch sphere is with probably 1 minus 4/3 p, you stay where you are with probably 4/3 p, you're mapped to the identity in the middle. And so in other words, you're mapped to this point, let's see, like 4/3 p of the way from here to the middle of the Bloch sphere. So the whole sphere is sort of uniformly being shrunk. Slightly, hopefully p is small, so it's only shrunk a little bit. That's the idea of the polarizing noise model. And often this is what we assume that we have because we just don't understand. So for example, if you're trying to simulate a CNOT gate with depolarizing noise, what we say is with probably 1 minus p, nothing happens. With probably p over 15, each of the two non-trivial 2-qubit polyoperators, so xx, xy, xz, xi, xi, xx, xy, xz, yi, yx, yz, and so on. So there's 15 of those. And you say with probably p over 15, each of them occurs. So that would be the dumbest model for a CNOT gate. So the perfect CNOT gate is applied, and then this channel happens. Of course, if you wanted to, you could like these probabilities don't have to be equal. You can make them non-equal if you wanted to. It turns out it's not that easy to take advantage of that kind of asymmetry in practice, but yeah. So that's depolarizing noise. It's a very popular noise model. If you don't know anything about your system, you just model as depolarizing. If you know a little bit more, you get to what's called dephasing noise. So dephasing noise, it's very similar. So the density matrix rho with probably 1 minus p is left alone, probably p, z are recursive both. So z is applied to the density matrix. And so on the Bloch sphere, what happens is, well here. Oh, okay, I have it written now. So on the Bloch sphere, the z coordinate on the Bloch sphere is unchanged when you conjugate it with z. The y coordinate and the x coordinate are both they're flipped because they x and y anti-commute with z, and so you'll pull down a factor of 2p. Maybe I say p. I don't know. It's either 1 minus p or 1 minus 2p. Here, and so basically the x and the y coordinates are shrunk, but the z coordinate is left alone on the Bloch sphere. And then this is actually usually a better physical model for noise, because often you have often your qubit is encoded as 2 different energy levels in an atom or an artificial atom, and this kind of dephasing noise comes from the fact that 0 and 1 are have different energies, and so they're processing at different rates, and you don't know exactly what that rate is because there could be energy shifts because of something in the environment, or just because you don't understand the system quite that well. And that gives you dephasing noise, and that's really relatively easy compared to going from 1 to 0. Or a noise that, like an X noise, which also goes from here to here, from here to here, is harder because that actually involves changes of the energy. And so that energy has to come from somewhere in the environment or go out somewhere in the environment. Whereas this dephasing noise could just happen very easily because just you don't know what's going on. No energy has to change. You can stay in Ket 1 or stay in Ket 0. So in some practical systems, I mean, the dephasing noise rate is like 10 times higher than the depolarizing noise rate, roughly. So there's often a fairly large asymmetry. And this is what we talk about. So there's jargon here that's called T2 time. So T2 time is the time it takes for a system to lose its coherence in the z direction because it's become completely dephased. And so really this is saying that we have at all times we have a stochastic process that's dephasing the qubits, and so therefore as little t goes higher, the probability of the qubit being dephased grows. And it's just an exponential process where when little t becomes equal to the T2 time, and the probability of a z error is like 1 minus 1 over e, which is like 60% or something. And we define that to be the T2 time. It's the time it takes for your qubit to be 60% dephased, or 60% in phase, whatever. Yes, and in many systems, this is the dominant noise. This is the dominant noise process.
What's the meaning of dephase here?
Oh, so dephase, because when you apply a z error to, if you look at like alpha 0, plus beta 1, and I apply a z error to it, you get alpha 0 minus beta 1, right? And so the phase between the 0 state and the 1 state is lost. Or if you apply e to the I theta z, where theta is like epsilon, theta is small, you get cosine, what does this give you? Yes, you get alpha 0 plus e to the I theta beta 1. Something like that. 2 theta. So if theta is small, I don't know, so that's why it's called dephasing. It's because you're losing the relative phase information between these two states. Yeah. Right, okay, so it often dominates noise on resting qubits. I guess the problem is when you start applying gates, then like any interesting gate, like a Hadamard gate, it mixes the z bases and the x bases. So even if your dominant noise rate even if your dominant noise process on resting qubits is z's, whenever you try to do something interesting, all of a sudden that's being turned down. That z error rate is being turned into other kinds of error rates. And so that's again why probably we in practice use depolarizing noise models, because even if the base noise is dephasing, very quickly it turns into other kinds of noise. Again, I mean, these are sort of abstractions for more complicated noise models that we don't understand. The last two ones here is leakage errors, where when the qubit is lost, which you can't. It's not explained by Pauli operator, but it's still easy to model in your classical computer, because you just have instead of using plain Gottesman-Kenilly, you just have some other flag which says is the qubit there or not. I guess. Yeah.
So I have another question regarding that dephasing thing. So
Yeah.
when you have this, say, block vector, and we start with some superposition of 0 and 1, so we are basically on the equator, right?
Yeah.
Block. And then it starts to rotate. That's what we are calling that it's getting dephased.
Well, so just rotating would be okay, because that would take a pure state to a pure state. Well, I guess what happens here is if there's uncertainty in the speed of the rotation, like maybe it's rotating this direction with probably 1/2, or it's rotating in this direction with probably 1/2, then the density matrix would be half this plus half
It
this,
would be
so that'd be in the
somewhere
middle.
between,
Yeah, exactly. Yeah, and like that's what this calculation is doing. It's saying if you have some probability density over the angle by which you're rotated, provided that this density is equal, so it's 1/2, 1/2, or it's equal in opposite directions, and when you compute this integral of the probability times the noise, you end up with a dephasing channel. So it can handle more complicated distributions of rotation angles. They still turn out to be just dephasing. So I'm out of time. The last one I could mention is amplitude damping. So this is when a qubit relaxes from 1 to 0. I can mention this more next time, or read it. It happens. So I guess what's important here is it's called T1 time. So T1 time is larger than T2 time. It's the amount of time it takes for the system to relax to the ground state, back to 0.